Good afternoon, everyone, and welcome to the NITheCS Colloquium, which will be given by Professor Sahal Yacoob from University of Cape Town, and he is an active member of the Atlas Collaboration. And the talk is going to be about the W-Boson by any other mass, and Professor Yacoob is an experimental particle physicist and associate professor at UCT, where he has been since 2015, and he was the leader of the local Atlas experimental group. And this group, to those who are not aware, is collects and analyzes the data from the proton-proton collisions at CERN at the Large Hadron Collider. Professor Yacoob is one of the co-author of this Atlas collaboration on the famous Higgs discovery paper. And before kind of joining the Atlas collaboration, Professor Yacoob have done his PhD with focusing on the measurement of the mass of the W boson at the Tevatron experiment. In addition to his kind of professional interest in the fundamental physics, Sahal is committed to the increasing the diversity in science and has led many outreach and diversity initiatives. So Sahal, take it over.
Oh, thank you, Ilya. I thought I was muted and I was not, but I guess there wasn't too much feedback. Thanks to everyone for joining. I was asked to talk about a new measurement that came out of the CDF collaboration. And as you've heard, I'm not a member of the CDF collaboration. I'm a member of Atlas, and I was a member of the D0 collaboration. So really what I've pitched this talk as is an intro, so you can follow along a more detailed talk from CDF, which is the collaboration that released this new measurement recently. It was on the 8th of April of this year. There's a publicly available webinar hosted by CERN. And Professor Kotwal from Duke goes through the details of what is a very difficult measurement. What I'm going to do is describe particle physics a little bit to set the stage. And then I'm gonna take you back in a bit of a time machine to when I did my PhD and the challenges and my understanding of what it takes and why it's important to measure the mass of the W boson, and then talk about the new result and why it's particularly nice. I'm not entirely sure about the timing. If you have questions, Ilya, I don't know how you normally handle this, but I guess type them into the chat. And if there's something that needs an interruption, you'll intervene and let me know. Can you confirm that that's how it'll work, or have I got that wrong?
Yes, yeah, that's exactly how we're going to do it. If there will be some urgent questions, I will probably disturb you, but otherwise we will leave questions at the end. And following the tradition which Francesco recently set up, we will not record the Q&A session and only will record the main talk.
Okay, perfect. So you have something to expect. I'm going to be a bit more detailed than this first slide. But when we talk about particle physics, what I mean by particles are right at the end down here. These are the constituents of everything else that, as far as we know, have no internal structure. So, this is a talk for NITheCS. So I assume everyone's aware of atoms. And an atom has electrons orbiting a nucleus. The electrons are our first fundamental particle with no internal structure. Nuclei are made up of protons and neutrons, which themselves are made up of quarks. So the quarks and the electrons are what we consider our fundamental matter particles. And it's important to note, just in case anyone's not clear, this is always, as far as we can test it. So theoretically, the theories work with them being infinitely small and massless, and experimentally this has been tested down to a limit, but of course we could always find new information. So our full set of elementary particles, or our different Lego blocks that we have out of which we can build the universe, is represented on this wheel In red, on the top hemisphere, we have the different types of quarks. In green, in the bottom, we have the different leptons. And in the central blue circle, we have the gauge bosons. So the gauge bosons are the force-carrying particles, and the interactions between the matter particles on the outside and the force-carrying particles on the inside are how we have all the interactions of nature. The quarks that make up the protons and neutrons are the up and down quarks. So we have up, charm, and top, down, strange, and bottom, and they're paired up. The up and the down are related, the charm and the strange are related, and the top and the bottom are related. Similarly, we have electrons, which have an associated neutrino, muons, which have an associated neutrino, and tau leptons, which have an associated neutrino. The photon is responsible for the electromagnetic force, the gluon for the strong force that holds quarks together inside protons and neutrons. The W and the Z bosons carry different parts of the weak force, which is actually part of a more broadly defined electroweak force that includes the photon, the W boson, and the Z boson. So this is our first mention of the W boson. The W boson is a charged force-carrying particle of the weak force. So there is a W plus and a W minus. All the other force-carrying particles are neutral. There we go. We have our matter fermions and our boson force carriers. We have our theory of how to fit all our pieces together. This is it written in shorthand. This is the longer version. In principle, this is the Lagrangian density. Sorry, let me go back. I got slightly off. This is the Lagrangian density that you're looking at. So out of this, we can get all the dynamics of the standard model. This Lagrangian density and the standard model, which describes almost everything we've been able to measure really, really well, has kind of a big hole. For mathematical consistency, just to be able to compute anything, it requires that the gauge bosons, so the W and the Z bosons, and all the quarks be uniquely massless in the theory. We find when we discover these particles and measuring them that they're quite heavy. The W boson has a mass of about 80 times the mass of the proton. The top quark has a mass that's even higher than that. I think it's about 140 times the mass of a proton. And so this presented a big problem because you had a theory that could describe the data incredibly well, but was inconsistent in this quite fundamental way. And one of the ways around that was to introduce a new field so that masses were obtained by these massive particles via their interaction with the field. So our last piece in the center is our Higgs boson, which provides masses of different particles. So the W boson interacts with the Higgs field, and in that interaction, it gains a rest energy, which becomes its mass. The top quark does as well, and they both do so very, very strongly. The lighter particles couple to the Higgs loosely. So now we have our full set of Lego blocks, the pieces we stick together in order to make the universe, and our full set of interactions to describe the universe. And this is what we're trying to describe. Right? I hope that all of you are here because you want to understand nature, and part of it is, where does it all come from? And most of our evidence tells us that there was some event, a big bang, which started everything off with a clock, and then matter was created, matter and antimatter together. There were quantum fluctuations. as the universe expanded and cooled, things got frozen in, and eventually gravity caused the development of structure, and we end up out here. And we're out here, part of the process. Of course, this is more of a cosmology type of image, but we're a part of this process of trying to understand how we ended up here. And one of the unknowns is, if we believe the most likely description of this, that we were created, the matter was created out of nothingness in the Big Bang, we should see an equal amount of matter and antimatter. And with the interactions of the universe, the interactions that are allowed within the standard model, there should be more antimatter to account for the amount of matter we see in the world, in the universe, and there isn't. So while I've started by telling you, here's this thing, it works really well, we don't describe everything, we struggle with antimatter, we struggle with the matter we have, because this wheel that I've been talking to you about fits into the little red pi wedge. 21% of the rest of what's in the universe is dark matter, by which we mean it is something else that is not any of these particles. And then 75% of the energy mass of the universe is dark energy, and we have no idea what that is. And finally, in this model, we completely ignore gravity. So we have no gravitational interaction, which is weird, because gravity is probably the first interaction that we've known about as a species. And so that's probably, for me, the biggest hole in the standard model. And when I talk about the other holes in the standard model, they're all related to gravitational things. We see this in cosmology, looking at universes, antimatter, dark energy. Okay, so that doesn't mean the standard model doesn't work. It works really well in its area of applicability. We just like it to have a broader area of applicability. So in our field, we talk about it being an effective theory, right? It works now, it describes the things we can measure, but it doesn't describe everything. And an example of this, again, from the particle physics world, is to describe beta decay. So beta decay is where a neutron decays to a proton, an antineutrino, and an electron. And Fermi had a theory of the weak interactions where this was a direct interaction that took place. In terms of the current standard model and the electroweak theory, there is an intermediate particle, which is the W-Boson in this case. It's quite nice because we're talking about the W-Boson, that mediates this interaction. So in this way, our description of the universe with the W-Bosons, Z-Bosons, gammas, and gluons mediating things could be something that at the orders of energy of the interactions with which we can look at the world works really well. But as we are able to look at the world at higher energies and break it down more, we could find that this is just an effective theory on something else, similar to how Fermi's theory was successful at low energies. It's kind of also similar to Newtonian gravity, which works really well where it's needed, where we know it works, but isn't the right thing to use looking when we're trying to study black holes and relativity. Okay, so that's the general introduction to particle physics. As we look at these particles, the Higgs boson was discovered on the 4th of July, 2012. And actually, in a couple of weeks, on the 4th of July, 2022, there are a number of commemorative events. There's one hosted by CERN, there's one from a collaboration of African physicists, and there's one from the SAIP, and you should look out for that. I'm sure they'll talk a lot about fundamental physics and the value that's come out of the work since the discovery of the Higgs boson. Prior to the discovery of the Higgs boson, The top quark was discovered in 1995. So between 1995 and 2012, no new particles were discovered in the realm of particle physics. The theory was all kind of there. We had this idea that there was this Higgs field that could give these particles masses, but until the Higgs boson was discovered, we didn't know if that was correct. In that gap from 1995 to 2012, the tau neutrino was first observed, but it's one of these things that it would have been more of a shock if it hadn't been observed. Neutrinos are particularly hard to see. And so once the tau lepton was discovered, the tau neutrino observation was newsworthy, but not earth-shattering. So we're going to go back into a little time machine to early 2012. The Higgs boson discovery was the 4th of July. So prior to the 4th of July, 2012, a young, not Professor Sahal Yacoob, was working at the University of KwaZulu-Natal and preparing talks about a W-Boson mass measurement at D0. And at the time, this is what the standard model looked like. So this is the same information that was in the wheels we had that I showed you earlier. We have our force-carrying particles, our matter particles, and then our Higgs boson yet to be confirmed. There's another nice slide from 10 years ago, which these have probably gotten a bit better in the meantime, but I like showing this and I decided to keep it in here. This is just showing how well the standard model works in the description of the electroweak interactions. I'm going to take a minute to describe this. This is the prediction of a parameter from a fit to basically all applicable measurements, minus the actual direct measurement divided by the uncertainty in that measurement. And you can see that for most of the parameters within the standard model, this works really well. So when I say the standard model works really well, it describes the data very well. This is kind of what I'm talking about, right? The deviations between the measured values and the best fit values, if we don't include those direct measurements, are really, really good considering the number of measurements. So remember, we're back in a pre-Higgs world. This is still early 2012, and the standard model does not predict, even with the hypothesis of a Higgs boson, the masses of particles. And particularly with the W boson, there's a term with radiative corrections. So out here we have radiative corrections. Ooh, that's not where I want to be. There we go. Out here we have radiative corrections. It's the delta R. And what this means is that as the W boson down here, this little green coil is a W boson existing through time. And it exists, and part of its eigenvalues for existing are a well-defined mass. And as it's existing, there's a little quantum fluctuation, and it creates a quark-antiquark pair, which then recombines, and it continues as a W boson along its merry little way. And a little while later, it can also radiate a Higgs boson, which it then reabsorbs and continues on its merry little way. And the fact that these quantum fluctuations can happen has an effect on what we measure for the W boson mass, because this green telephone wire bit is a diagrammatic representation of the existence of the particle. So these little delta R corrections come from the fact that these quantum fluctuations happen here. And the biggest corrections to the W boson mass are from the coupling to the Higgs, because the W boson is heavy, and from the top quark mass. And that's technically due to the rather large mass difference between the top quark and the B quark. So what we can do with this, again, in a world before the W boson existed, is we could take measurements of the W mass and measurements of the top mass, and using those values and their uncertainties, predict what the standard model says the Higgs mass should be. And this is what the data looks like if we look at this, right? What we have here is in blue, the measurements from the Large Electron-Positron Collider and the Tevatron for the mass of the top quark and the mass of the W boson with their 1 sigma uncertainty. This is an older measurement. So the point of this plot was to show the improvement from LEP1 and the Stanford detector to LEP2 and the Tevatron data. And you see that the W boson mass constraint has become much, much tighter, while the, sorry, I got that backwards. The top mass constraint has become much, much tighter, but the W boson mass constraint is still about the same in this plot. Pay attention to the scales though. We need to know the W boson mass to a much higher precision to have a similar constraint till we get from quite a large uncertainty on the top mass. And in this world, what we're looking at is something telling us that the Higgs mass, let me back up a little bit. So this is top mass on the x-axis, W mass on the y-axis, and then lines of consistent Higgs mass drawn on here. So this is telling us if the Higgs boson exists and it has a mass of 114 GeV, and the top mass is 175 GeV, then the W boson mass should be whatever this value is, right? So if the Higgs mass is 300 GeV and the top mass is 175 GeV, then the W mass should be down here. So we superimpose onto that the measurements of the top and the W mass, and we see that there's a little region here where this circle intersects with the allowed values of the Higgs mass. Okay, above this line had already been excluded experimentally. In the yellow bits had been excluded experimentally. And so there's this little region because we've measured the top mass. We know it's in this area. We've measured the W mass. We know it's here. And so the constraint from these propagators, what I was talking about on the last slide, tells us that if the Higgs boson exists and it is what we think it should be, it must exist in that little window. This is more of the same. So these are the same limits described differently. And basically you can see that the Higgs mass needed to be between 115 and 127 GeV. And on the 4th of July, 2012, a Higgs boson was discovered with a mass of 125 GeV. And this closed the circle like on the W mass. And most research focus switched to details of the Higgs boson. What can we learn about the Higgs boson? What else is out there? And then suddenly, on the 8th of April, 2022, the CDF Collaboration released a new measurement of the W mass, which was different to the world average. Very different, and claiming to be very, very precise. So this is the new result. You can see it down here on the right. The gray bar is the standard model. These are previous measurements. So the D02 experiment was what I worked on. The Atlas experiment came out a little bit after that. Between the Atlas experiment and the CDF2 experimental results, there was a measurement from LHCb that was kind of in agreement with the gray bar, with the standard model. There were issues with the CDF publication which is why it's not included in here. Basically, they submitted it for publication before the LHCb result was out, but by the time they got published, the LHCb result was out. That's why that's not on this table. But you can see that this is a claim to be the most precise measurement ever, and significantly far from what the standard model tells us the mass of the W boson should be. And so that's kind of a big deal. What does that mean really going forward if they're right? Well, in the same way that before there was a Higgs boson, I said we could use measurements of the W, the top, and the Higgs to constrain the Higgs boson. Now we take measurements of the W, the top, and the Higgs, which we know exists, and we're constraining the existence of any unknown new particle. So that's what's happening. Okay, so when we look at, it's on the next slide. So we look at an update to the same type of plot that I showed you previously. We have the top mass on the x-axis. We have the W mass on the y-axis. This gray circle, the gray circle down here is the old circle I showed you before, with the standard model just outside 1 sigma away, which doesn't bother us too much. The red circle is the new CDF2 measurement. And then this is parameterized in terms of supersymmetry, even though supersymmetry is a disfavored model of new physics, but it's a nice way to parameterize deviations from the standard model. So let me try to explain what this arrow in this green area means. So this is the standard model as we have it. If there are new particles that exist that we haven't seen yet, and they're very heavy, their effect on what we can measure right now is very small. So what we should observe is really close to the standard model. That's why down here, this is marked as heavy supersymmetry. If these unknown particles have lower masses, they're accessible at lower energies, then they will start to have effects on things we can measure now earlier. So up here in the light supersymmetry area, we're saying, actually, we should see some effect, right? And so what's happening here is basically the fact that this new W mass moves this circle so far away from the standard model leaves us with two possibilities. Either this is evidence that there are undiscovered particles that we're on the cusp of being able to see, or even we have already seen the effect of their existence in this W mass, or there's been a rather large fluctuation, or finally, somebody made a mistake. I want to point out that this data was taken, they stopped taking data over 10 years before publishing this measurement. So the experimental group spent an incredibly long time trying to understand the detector and their uncertainties and get everything right. I hope they haven't made a mistake. They're certainly confident. But of course, when you see something like this for the first time and no one else has seen this type of discrepancy, that is something that goes through one's head. So this is their final uncertainty table. For a total uncertainty of 9.4 MeV on a mass of, let's go back, 80,433.5, right? So this is what the measurement was, and it's worth highlighting the scale. So you're measuring a value of 80,000 with an uncertainty of 10. So these are the various contributions. Probably doesn't mean much to you. And if it does, you certainly want to be watching Ashitash's talk and not mine. For the rest of the talk, I'm going to talk a little bit about the Tevatron and the difficulties and the mechanisms of doing this measurement. So the Tevatron was a proton-anti-proton collider, which is different to the LHC, which is a proton-proton collider. So in order to produce a W-boson, a quark and an antiquark from the proton and antiproton going past each other would collide, produce a W-boson, and that W-boson would decay predominantly back into two quarks. When it decays back into two quarks, that's a very challenging experimental channel in which to measure the mass of the W-boson, because quarks are very hard to measure experimentally in particle physics experiments. Some of the time, the W-boson will decay to a muon and a muon neutrino, or an electron and an electron neutrino. And those are the events that were detected by D0 when I did this work, and are detected by CDF for their analysis. Of course, we don't get the protons and antiprotons coming through one at a time. And there's also the rest of the proton and the antiproton to deal with after the quark and the antiquark collide. So we have the spectator quarks, which are the remnants of the proton and antiproton that are still in the detector and could still contribute to what is measured, and additional proton-antiproton collisions, because the collisions happen in bunches. So there are bunches of protons that collide with bunches of antiprotons. And these extra energy bits are in the detector and need to be properly accounted for. So once the W-boson is produced and decays into an electron and a neutrino, the electron is quite well detected by the detector. So here we have an electron moving out from where it was produced. It'll be measured as a track, signified by this straight line. And then in our calorimeters, signified by this bump, where the electron deposits its energy. There are some underlying event energy that will be distributed around the entirety of the detector. There's also the neutrino. Now, the problem with the neutrino is that neutrinos don't interact with the world. They're very hard to detect, and they escape the detector essentially undetected. And that is a huge problem. So as a proxy for the energy of the neutrino, hadronic colliders use the missing transverse momentum, which is often signified as missing ET, and I might even talk about it as missing transverse energy, but the naming has changed in the last 10 years. So the missing transverse momentum, in order to calculate that, you have to measure all the momentum in all the channels of the detector, add them up in a vector sum, and attribute whatever's missing as the momentum of the neutrino. And those two statements are why measuring the W mass at a hadron collider is incredibly difficult, because you need to understand all aspects of your detector incredibly well. Otherwise, you get a really bad proxy for the neutrino PT. What do we use to measure the W mass? You can use just the PT spectrum of the electron. This is a simulation to show a couple of options. If we had a perfect detector with no experimental uncertainties, and our W bosons were always produced at rest, we would get this black histogram for the electron PT spectrum. And we could measure this, and the position of this peak would move slightly to one side or the other, depending on the mass of the W boson. Unfortunately, W bosons aren't produced at rest. They have some transverse momentum when they're produced, and that broadens out this distribution to the yellow shape, which again will move a little bit to the left and to the right, depending on the W mass, but you can see that it is just less defined. And then if we add detector effects onto the PT spectrum of the electron, it changes it a little bit, but not too much. There's a second distribution that we used at D0 called the transverse mass. And this takes into account the electron transverse momentum spectrum and the missing transverse momentum spectrum and combines them into a mass-like variable that is missing the momentum along the beam direction. Because the beam is coming in and going out, we don't have that information. And in that case, you see, if we have a perfect detector and we're producing W's at rest, we get the black histogram. Adding a transverse momentum to the produced W bosons will give us the yellow histogram. So if we measure the transverse mass, the inherent PT distribution of the W boson doesn't make a big difference, but the red dots, the detector effects, make a huge difference because we have to measure every little bit of the detector. CDF in their analysis also just did a missing transverse momentum distribution. So that's like the PT distribution of the electron. They did one for the neutrino as well, and it would have a similar type of behavior. So there are three distributions: the PT of the electron, the PT of the missing transverse momentum, the transverse mass distribution, and you can make each of these three distributions for electrons or muons. So essentially, there are 6 distributions that are used to measure the W mass from one data sample. So we build up a set of templates from a Monte Carlo generator that describes what's happening, a very detailed detector simulation that is purpose-built for the W mass, and then you get templates like this. So this is to illustrate how different a template with everything built into it is for a change of 1 GeV. We confront these templates with the data, but in the building of these templates, we have to estimate the uncertainty. So back when I did this work, the details of the event generation, so how well we understood the transverse momentum of the W boson and the radiation of these photons, was a 5 to 11 MeV event, MeV effect, sorry. And the emission of photons was another 7 MeV event. And then finally, I want to say that we use the Z boson a lot. So back when I did this work, you can see the little Einstein measuring his W boson with a Z boson behind him. And because CDF, like D0, did a lot of work depending on the production and decay of Z bosons. So the Z boson is a neutral particle that is almost the mass of the W boson. So if a Z boson is produced, it decays into an electron and a positron, not an electron and a neutrino. We can measure the electron really well. We can measure the positron really well. And that is the calibration sample that we use. So for D0, a lot of work was done using Z bosons to get our calibrations right, to enable us to measure the W boson. Because CDF was a different detector with a better tracking system, they could calibrate on Z bosons and a particle called the J-psi that is at a different energy range, and that gave them a lot of freedom to reduce those uncertainties. I mostly left this slide here to talk about the number of channels. So on D0 for the calorimeter, it was approximately 46,000 channels that we had to understand. This diagram is basically outward from an interaction point here to the many channels of the calorimeter. And CDF would have had a similarly large number of channels. And in order to get the information about the neutrino, one has to understand or simulate this really well. And then in our final kind of journey in our time machine, this was my final slide. Back in 2012, the expectation was that we were going to hit up against a theoretical systematic uncertainty of 11 MeV, and maybe at 1,000 inverse picobonds, we'd be down there with measurements. So this is the last CDF measurement with 2 inverse picobonds, or this is us with 2 inverse picobonds. Oops, we're out there. And at the time, we thought we were really coming up against the theoretical limit. In the meantime, there have been advances in the theory, advances in how CDF understand their detector. And so everything has changed in 10 years. Science progresses. I want to take us back to current times. Stop here. So again, I hope this has been illuminating. It's not really my work. So really go to the link on slide 2 and watch Ashutosh talk about it and all the mini checks they've done. And I hope this has given you an idea of why this was big news and why this was important. It's a measurement that's considered a tour de force. You know, it's like somebody, I don't know, swimming from Cape Town to Australia, right? That's how it's seen. We know it's a hard thing to do. And then to do it and get a number that is so unexpected when it has been measured a number of times is quite shocking. Yeah, take care. Thank you very much for coming.
Thank you very much, Sahal, for very interesting talk and kind of for a little kind of historical excursus, and obviously everyone who are interested in kind of the current state of the affairs can go and follow the talk, the links to which you have provided. Okay,